We will solve another problem on bending stress in beams. Examination problem. The question goes like this: a beam simply supported with timber as the material, has a span of 6 meters. It carries a UDL of 12 kN per meter, uniformly distributed. It carries a UDL of 12 kN per meter throughout the span. And a concentrated load of 9 kN. At 2.5 meter from left support. If the stress in timber is not to exceed 8 Newton per meter square, if the stress in timber is not to exceed 8 Newton per meter square, design a suitable section. Rectangular section with depth equal to twice the width. Yes. So this is the problem. So here you can see that it is a simply supported beam, material is timber, span is 6 meters. So sketch is not given, let us draw the sketch. So this is the simply supported timber beam. It spans 6 meters. Like this. It carries a UDL of 12 kN per meter, like this, over the entire span, and concentrated load of 9 kN at 2.5 meter from depth support. Depth support is A. So 2.5 meter means somewhere here 9 kN load is there. This is 2.5 meters. If the stress in the timber is not to exceed 8 Newton per millimeter square, means F value has given, maximum value of F is 8 Newton per millimeter square. We have to find the dimensions of the rectangular section. So, but he has given depth equal to twice the width. So that means this beam is a rectangular beam whose depth is equal to 2 times the width. I will take B as the depth, B as the width. So he has given that B is equal to 2 times B. This is given in the problem. Even if it has not given, it can assume. Normally 1.5 to 2 times 3, we are going to take as the depth. So since it is a rectangular section, your center of gravity, the center will lie here exactly, and neutral axis passes through the center. So in this case, maximum bending stress occurs at the farthest fiber, and both central compression side is equal, because if you plot the bending stress diagram, at neutral axis it is 0, and your compressive bending stress and tensile bending stress both are equal here, because the section is symmetrical. So this is above the neutral axis. Since it is simply supported beam, it is subjected to compression bending stress. Below the neutral axis, it is subjected to tension bending stress. So in this case, FC is equal to FT, and maximum we have given So we have to find the suitable section for B. That is, we have to find out B and D. So they are the amounts here. I need to find B and D. Once you find B or D, the other can be found out using this relation. We have given that D is equal to 2 times D. Of course, here you know that the maximum bending stress will occur at the point of maximum bending moment. So in this problem, we have to first find out where the maximum bending moment, at what point maximum bending moment occurs, and we have to find that value. You can observe here that under the load, because it carries a UDL as well as a concentrated load, so the profile of the bending moment diagram in this case, so you know how to draw the BMD. The profile in this case, I will draw the profile. So this is how it is given. If you draw the profile of the BMD, you know that bending moment diagram is a parabola for UDL and it's a straight line for a concentrated load. So here it is 0, bending moment is 0, here is bending moment is 0, whereas here it has got the maximum value like this, then it will come down. So it's a parabola, this is a parabola. So that means you can observe here maximum bending moment occurs at the point C. So here this is value of MC. This is the bending moment, positive subjected to sagging bending moment throughout. Now if you draw this is the BMD. So this MC becomes the max. If you draw the shear force diagram, so for this typical shear force diagram on the right. So here shear force from here to here. So you will be having something like this. Then this is a typical shear force diagram. Of course, values I have not written here. Yeah, this is negative. This is something like this. Okay. So I have not written the values. So shear force diagram. So why I have written this typically is, you should know where the maximum bending moment occurs. So normally maximum bending moment occurs at the point when the shear force changes its sign, or where the shear force is 0. Here in this case, since concentrated load is acting at C, so there the value of maximum bending moment occurs. So now let us find out the value of MC now. This is 9 kN, this is 12 kN per meter. So we need to find the reactions. So this distance is 2.5 meter, so this becomes 3.5, total is 6 meters. So we need to find the reactions RA and RB by using equilibrium equations. Let us use equilibrium equations. RA plus RB is equal to total load, which is 12 into 6, so that is 72 plus 9, 81. This one equation. The other equation is sigma MA is equal to 0. Considering clockwise positive and clockwise negative. 9 into 2.5 plus 12 into 6, that is 72 into distance from A to midpoint of UDL is 3 meters, converted into 3, minus RB into 6 is equal to 0. So RB will be according to this, you can find out the value of reaction RB. So the value here is RB will be 9 into 2.5 plus 72 into 3 divided by 6, 39.75. Then therefore RB is equal to 81 minus 39.75, so which becomes 41.25. So RA is 41.25 kilonewton, RB is 39.75 kilonewton. So reactions, multiply the reactions, now you can calculate the maximum bending moment at C. So MC value by taking to the left side of the section, you calculate the bending moment at C, left side of the section. This reaction is acting upwards, bending moment is positive. So 41.25 into 2.5 minus UDL is there from here to here. 12 into distance is 2.5, that is intensity multiplied by distance, into the accident distance of 2.5 by 2, that is 1.25. So this is the maximum bending moment at C. So if you simplify this, 41.25 into 2.5 minus of 12 into 2.5 into 1.25. So it becomes 65.625. 65.625 kilonewton meter. So this is the maximum value of bending moment where you have got. So this acts at the point, this develops at the point C now. So this MC we have to take it as max. To find the load, of course load is given. To find the dimensions of the beam, we need this value. So let me convert this into Newton millimeter. So 65.625 into 10 power 6 Newton. So this is the value of max. Then I need the value of moment of inertia about the neutral axis. INA is BDQ by 12. We know for a rectangular section it is BDQ by 12. Since he has given here D is equal to 2 times B, 2 unknowns should reduce it to 1 unknown. B into 2B whole cube by 12, and it is 8 by 12 into B power 4, or you can written as 2 by 3 B power 4. This is I value. Then the value of F, we have given maximum value of F. Here Ft is equal to Fc is equal to F max, which is 8 Newton per mm square, and the value of Y max. Y is Y max here. Y max distance is this. Here in this case, Y max will be equal to D by 2. D by 2 can be written as B only. So Y max is equal to B because D is equal to 2 times B. Now these are the 4 parameters we require to substitute in the pure bending equation. Pure bending equation. The pure bending equation says M by I is equal to F by I. Okay. So M here is MC 65.625 into 10 power 6 divided by I is in terms of B 2 by 3 B power 4 is equal to F value is 8, Y value is B. Now from this equation we can find out B. Of course this 3 goes to numerator, 3 into 65.625 into 10 power 6 divided by 2 will be there. P cube it becomes. B power 4 B means 1 B will get cancelled, is equal to 8. So from this you can solve for B cube and then B. So let us see what is the value of B here. So 3 into 65.625 into 10 power 6 divided by 16. This is B cube. So we have to take cube root of this. Yes, we have to take cube root of this. Cube root of this will be 230.86. 230.86 mm. So this is the width of the beam. So once you know the width of the beam, depth of the beam can be taken as 2 times b, which is into 2, 461.72. 461.72 millimeters. This is the depth of the beam. That means, in order to keep the beam safe, that means the value of this bending stress, if it should not exceed 8 Newton per mm square, then the dimensions of the beam should be kept as 230.86 by 461.72, or you can round it off. The value you can have the beam as 231 mm by 462 mm. Then it will be safe. This is the value of the section of the beam. So this is how we have to do. So first we have to compute where the bending moment is maximum. calculate that value after finding the reactions. Then you take that value as the maximum bending moment value. I value you calculate for the given cross section. Stress value is given, maximum stress value. Y max value you can get from the section. So once you substitute in this fluid bending equation, N1 can be found. So like this, they can give the data. So many data are there here. So depending on the problem, that means cross section will be unknown, or stress value will be unknown, or moment value may be unknown, load value may be unknown. So like this, different parameters will be there in any problem. So you have to understand what is the clear data given. Then use the formula, fluid bending equation. In this fluid bending equation, only one unknown will be there that we have to compute.